All right, welcome back after a wonderful long weekend. We had a glorious amount of sunshine, and I really hope you got outside, maybe rode a bike, and got your minds off of school for a little bit. But we're back. So now that we're back, we're going to be taking a look at our last of the integration topics that we're dealing with. This is the volume of an object created by rotating a graph around the x-axis. Let's take a look. So this has an incredible tie-in to the Riemann sums, and that's why I actually asked you to take a look at them, even though, as some of you pointed out, we've essentially done the same sort of thing before. I've got a line here, y equals x, and what I'm going to do is I'm going to chop it off at 4, going from 0 to 4, and I'm just going to take the area under that curve, and I'm going to rotate it around the x-axis. So I'm going to show this or demonstrate this by drawing in some of these Riemann sum type rectangles. And then you'll see that when we start to rotate things, each one of these rectangles rotated would become a disk. So to understand volume, we might, as I said, just take these and start rotating them. What shape is it going to make? Go on, say it out loud. You're right. It's going to look just like a cone. So I'm just taking some of those discs, I'm rotating them, and as you can see, we end up with that conical type of shape. It's on its side, I guess. So this creates this solid where y equals x is the line which is being rotated around, and as it rotates, each little piece of that area rotates and it ends up making this solid cone. So since this cone is made up of these little discs that I talked about, which remember in Riemann sums, if you read it right, you start off with a certain width, but then you redo it getting smaller and smaller and smaller until they're infinitely small. So essentially this cone is just made up from an infinite number of different sized circles. And we know that the basis of this is the area under that curve, which deals directly with antiderivatives or integration. Circles, the area of a circle is pi r squared, so essentially we're finding the area of every single one of these circles and we're putting them all together to create this cone. Pi is pi, and r can be found by doing the integral from 0 to 4 of the top curve, y equals x, take away the bottom curve, the x-axis, which is 0. So this kind of gives us a formula. Volume is equal to pi times the integral of the function squared, which is r squared. So we'll take a look at one example of this, and then I think it's fairly straightforward. We've done the exact same thing. It's just integration. I'll give you some homework and we'll get started on that. So this time, how about if we look at a parabola and go from 0 to 2? So here's our parabola. I'll draw in our 0 and 2 and show you that's the little piece that I'm going to rotate. I'm going to find the area. I'm going to rotate it around. So it's almost going to look like a cone, but it's more of a volcanic type of cone with curved in sides. Volume is equal to the pi times the radius squared, which is pi times the integral from 0 to 2 of x squared, because x squared is the function, and then I have to square that as the radius. I work this whole thing out, and I get 32 pi by 5 units cubed. Our homework, it's on page 531, 1 and 2b. Or not to be. Have fun. Talk to you soon on Wednesday.